In a world that feels like it's always on, always telling us to go, 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 what happens when your own brain just won't shut off? In this explainer, we're going to hack into our body's command center to understand a really powerful class of medications, CNS depressants. We'll dive into how they work, the very serious risks involved, and how they're used to bring back a delicate balance to our brain's chemistry.
So let's just start right here. Have you ever had that feeling? The racing thoughts, the staring at the ceiling at 3 a.m., or just that constant buzz of anxiety in the background? It's an incredibly common feeling, right? It's like you just can't find the off switch. Well, it turns out there's a very real biological reason for that.
Everything we're talking about, it all comes back to this, the central nervous system, or CNS. Think of it as the super complex network of your brain and spinal cord that controls, well, just about everything you think, feel, and do. It is the command center for your entire body.
Okay, so to really get how these drugs work, we first need to understand the brain's most basic balancing act. You can pretty much think of your brain's activity as this constant tug of war between go signals and stop signals, all firing thousands of times a second. All right, let's break this down. It really comes down to two key chemical messengers in the brain. On one side, you've got GABA. GABA is the brain's main inhibitory signal. This is the brakes. It's telling your brain cells, hey, calm down, stop firing. Then on the other side, you've got glutamate. That's the main excitatory signal, the gas pedal, telling neurons to get active and fire away. A healthy brain is all about keeping a perfect, dynamic balance between these two. But problems pop up when that balance gets thrown way off. Conditions like anxiety, insomnia, even seizures. They're often what happens when the gas pedal is floored. Way too much glutamate, and the brakes just aren't strong enough to keep things in check. So the entire goal of CNS depressants is to help get that balance back. So how do we do that? Well, the first big strategy is to make the brain's natural stop signal, GABA, more powerful. It's basically like giving the braking system a serious upgrade. Let's see how that works.
And this shows us two really famous classes of drugs that do this. First, you have benzodiazepines, or benzos. They work by making your GABA channels open up more often. So think of it like tapping the brakes frequently to keep things smooth and under control. Barbiturates, on the other hand, make those channels stay open for longer each time they open. That's like slamming the brake pedal to the floor and holding it there. It's a subtle difference, but it's a huge deal, and it's why barbiturates are generally much stronger and way riskier.
And inside that benzo family, there's basically a tool for every timeline. It all comes down to how long the drug's effects last. You've got short-acting ones like midazolam, which are great for quick medical procedures since they wear off fast. Then there are intermediate ones like alprazolam, which you probably know as Xanax, used for things like panic attacks, giving relief for just a few hours. And then you have the long-acting ones like diazepam or Valium, which stick around in the body for much longer, making them useful for chronic conditions like ongoing anxiety or seizure control. Okay, so that's strategy number one. Now let's switch gears. What if, instead of just boosting the stop signal, you could directly block the go signal from getting out of control in the first place? While this approach is absolutely critical for treating seizures. Now here's where it gets really cool. Seizures are basically neurons firing way, way too fast. To fire, they have to open these tiny little gates called sodium channels. What drugs like phenytoin do is they basically get in there and jam those gates shut. So the drug physically blocks the channel, and that stops the neuron from ever firing its go signal. No signal, no seizure. It's a pretty brilliant way to stop that electrical storm before it even starts. And there are a few key players that use this exact trick. Honestly, they've been total game changers for treating epilepsy. You have classics like phenytoin and carbamazepine that have been around for decades. Lamotrigine is another big one. And then there's valproic acid, which is kind of a powerhouse. It not only blocks these sodium channels, but also gives GABA a boost, so it's tackling the problem from both sides. Okay, it is so important to understand this next part. Messing with your brain's fundamental wiring, even when you have the best of intentions, is serious business. These are incredibly powerful tools, and they come with some major risks that have to be managed really, really carefully. And to make this super clear, let's just zoom in on one of those drugs we just talked about, phenytoin. Just looking at its list of side effects gives you a crystal clear picture of just how widespread the effects of these drugs can be. So to remember all the things phenytoin can do, med students actually use the word phenytoin itself as a mnemonic. And yeah, it's a long list. It covers everything from how it interacts with other drugs, to physical changes like enlarged gums, all the way to really serious stuff like birth defects, bone softening, and nerve damage. Now, this isn't to scare anyone, but it's to make the point that these are not medications you take lightly.
But out of all the risks that come with CNS depressants, there is one that stands head and shoulders above the rest. It's not about what one drug does by itself, but what happens when you start mixing them. It's called a synergistic effect, where 1 + 1 doesn't equal 2. It equals something like 10.
So here is the absolute bottom line, and the source material could not be clearer on this. The huge majority of fatal overdoses that involve drugs like benzodiazepines, they don't happen from the benzo by itself. They happen when it's combined with other depressants, and the most common ones by far are alcohol and opioids. See, each one slows down your breathing on its own, but when you take them together, they can slow it down so much that it just stops.
Which brings us to our final and maybe the most important piece of this whole puzzle. Treating these conditions isn't about finding some magic bullet. It's a super personalized, careful process of trying to restore the brain's natural balance.
Take seizures, for example. You can't just throw any old anti-seizure drug at the problem. A medicine that works perfectly for one type of seizure can actually make another type worse. Like you see here, for absence seizures, which can just look like someone staring into space, you need a very specific drug, like ethosuximide. But for focal seizures, which start in just one part of the brain, you'd want a totally different drug, like lamotrigine. The diagnosis has to be spot on.
And after the right drug is picked, the dosing follows this one simple, absolutely vital rule: start low and go slow. Doctors will start with the tiniest possible dose and then increase it very, very gradually, all while watching carefully for both the good effects and the bad ones. It's a slow, methodical process to find the perfect level for that one specific person. So as we've seen, these CNS depressants aren't just crude on-off switches. They're actually sophisticated tools designed to gently nudge an imbalanced system back where it's supposed to be. Whether it's by boosting the brain's brakes or blocking the go signal, these medicines are really our best shot at tuning the brain's incredibly complex chemistry. But it makes you wonder, as we learn more and more about the brain, what will the next generation of these tuning tools look like? Will we be able to target brain circuits with even more incredible precision? I guess only time will tell.